Figure 1 shows an operational amplifier used as an inverting amplifier. So we've got a diagram there in Figure 1 which shows the circuitry for the amplifier. Label Figure 1 with an X to show the point, which is a virtual earth. So a virtual earth is a point in the circuit which is not electrically connected to earth, but is held at approximately 0 volts. And that point is here, and your mark would be for getting that in the correct place. There aren't any other places on the circuit where that X can be placed. Name the input pin shown by a plus on the operational amplifier. So looking at this diagram, we can see that the pin with a plus is this one here. Now we call this the non-inverting inputs. And that's because it's held at 0 volts and it doesn't change from there, so there's no way that it can invert. So let's write that in the answer space. And that's the only thing that you can write down that will gain you a mark. Derive the expression for the inverting amplifier gain V out over V in equals minus RF over Rin. Now in order to do this, we need to look at the current flowing through various parts of the circuit. We're interested in the current flowing through the two resistors, and those two currents are going to be the same. Now we need to write down expressions for those currents, but we'll do that in the answer space. So the first fraction is going to be for the current in the resistor Rin, and we found this using the equation form of Ohm's law. And that will be equal to the difference in potential between Vx and V out divided by the resistance of Rf. So looking back at the diagram, we can see that for Rin, difference in potential will be between V in and the potential at x, which we're going to call Vx. And then for the current through Rf, we're doing the same thing, but the difference in potential between Vx and V out. So that's where the original form of that equation comes from. We now just need to rearrange. Before we do rearrange this, we can say that Vx is equal to 0 volts because it's a virtual earth. Now this simplifies the equation quite a bit because it removes Vx completely. And now all we need to do is rearrange the equation so that we have the voltages on one side and the resistances on the other. This form of the equation is stated in the question, but it's always good to write that down at the end so the examiner knows where we're trying to get to. Now, in terms of marks for this question, your first mark will be for correctly identifying that the currents in the resistors will be the same and substituting in a form of Ohm's law. And your second mark will be for making the necessary changes due to the fact that the potential at X is equal to 0 volts. So 2 marks there. Figure 2 shows the inverting amplifier modified to make a summing amplifier that is to form part of a 2-channel audio mixer. We've got figure 2 there. With that modification made, we now have a resistance value for RF of 150 kilo ohms. And you can see those 2 channels, one at 15 millivolts, one at minus 100 millivolts, with resistances of 7.5 kilo ohms and 30 kilo ohms. Calculate the voltage gain produced by channel 1. Now to calculate this, we need to use the following equation. So we have voltage gain in channel 1 is equal to minus RF over Rin1. So in that case, the voltage gain of that channel is going to be the negative of the ratio of the resistance Rf and the resistor Rin1, which in this case is 7.5 kilo ohms. So let's substitute in our values. Now here you could write your values in ohms and write 150,000 over 7,500, but the kilo ohms or the thousands would cancel, so you'd end up with 150 over 7.5 anyway. So we end up with a voltage gain of minus 20, and that doesn't have a unit because we've divided a value in ohms by another value in ohms. So your mark would be for correctly calculating this value. The mixer is tested using the input signals to channels 1 and 2 with the amplitude shown in figure 2. Calculate the amplitude of the output voltage V out produced in the test. Now for this calculation, we can start with the amplification factor A and say that this is equal to V out over V in, but also equal to minus Rf over Rin. We'll then rearrange this equation to make V out the subject. You'll notice here that I've got a fraction at the end saying V in over Rin, which is technically the total current input. So we have a look at how we can calculate that current from the original diagram. We have a voltage and a resistance on each branch for each channel. So if we divide that voltage by the resistance, we can get the current in that channel. Then since they join together at the point where X was originally, we can use Kirchhoff's first law to say that those currents are added together. So let's write this equation in another form. So I1 represents the current from channel 1 and I2 represents the current from channel 2. We can then make substitutions. Instead of saying I, we can say V over R and use the values that are provided to us. Then we need to make those substitutions. And that gives us a value of 0.2 volts, which we can write into the answer space. So for this question, you'll get 1 mark for getting to the correct form of the calculation, and a 2nd mark for getting the correct answer with the correct sign. And your answer must be positive. So 2 marks there. Describe how the function of the audio mixer could be improved by changing the 2 input resistors from fixed values to variable values. Now, the solution to this would be to use variable resistors. Now, saying this alone would not get you the mark, you need to explain why. And the answer here is that you can change the balance between the 2 signals, but on a continuous scale. You don't need to mention that it's a continuous scale to get the mark, but you need to talk about changing the balance between the signals. To secure that mark, you could also say that the gain could be changed easily, or that you can set the relative levels of the 2 channels, but they effectively mean the same thing. A die where dots on the faces of a cube indicate the numbers 1 to 6 is shown in figure 3 and is used in many games. So figure 3 shows one of those dice. A student makes an electronic version of this by feeding pulses from a pulse generator into a 4-bit binary counter. The circuit uses the first 3 outputs of the counter A, the least significant bit, B and C. By feeding the outputs from the counter through logic gates, the 7 LEDs shown in figure 4 can be made to display the numbers 1 to 6 in sequence. So we have figure 4 there with the typical arrangement of dots that you would find on the face of a die. Figure 5 shows the sequence of numbers. The black dots show which LEDs are lit for each of the numbers 1 to 6. The partially completed truth table in table 1 shows which of the LEDs L1 to L6 are on, logic 1, and which are off, logic 0, during the counting sequence. So we've got a pattern of zeros and ones there in the inputs and outputs for numbers 1 to 6. Complete table 1 to show the logic outputs for the lamps L1 and L6. Now, to be able to fill this table in for the 2 columns, we need to know what the patterns of dots would look like on the face of the die. So let's look at L1 to begin with. As we can see, L1 is the top left dots on the pattern, and on the faces of the dice, we can see that L1 is present for numbers 2 to 6. So for those dice, we need to show a 1, but for the number 1, we show a 0. And if you get those numbers correct, that will be your first mark. Let's now take a look at L6. We can see here that L6, the bottom right dot, is also present in all numbers except 1. So we put the same pattern of numbers in there. And your second mark will be for getting those numbers correct. So 2 marks there. Deduce the simplest Boolean expression that can be used to show how output L7 can be controlled by the logic inputs. So on this table, if we take a look at L7, in each of the individual rows, you'll notice that where there is a 1 for L7, there is a 0 for A. So if the number shown on the die is 1, A will show 0, and L7 will show 1. Whereas if the number shown on the die is 2, A will show 1, and L7 will show 0. So L7 and A are doing the opposite at all times. So we need to write that as a code in the answer space. So I've written L7 equals not A, which basically just means the signal on L7 is always the opposite of the input A. We can also write L7 equals A bar, which also means not A. Writing either L7 equals not A or L7 equals A bar will get you a mark, but nothing else. Figure 6 shows some of the input and output pins of the 4-bit binary counter. The datasheet for the counter indicates that the counter resets when the reset pin R is taken from logic 0 to logic 1. Draw on figure 6 the logic gate needed and the connections required from the outputs to the reset pin R on the counter so that the counter cycles as required. So let's look back at the table. Now in this table, you can see that in terms of the inputs A, B, and C, if we're using 2 inputs to give a certain number, 2 of the possible 3 combinations are already taken up, and those are in 4 and 6, where we've either got A and B or A and C. So for reset, we would need to use B and C. So let's make our wires come from B and C. Now for this to work, we need both B and C to be on, so we're going to need to use an AND gate. Then all we need to do is connect this background to R, so that the signals from B and C will activate R. So in terms of marks for this question, you get your first mark for selecting B and C, and your second mark for using a single 2-input AND gate. You could also get a mark for writing the correct reset code, but this is just an alternative, so 2 marks there. The outputs of both L3 and L4 can be written as brackets A.B.C bar plus brackets B bar.C. Figure 7 shows part of a logic circuit needed to represent this Boolean expression. Complete the logic circuit in Figure 7 by adding AND, OR, and NOT gates. So we've got Figure 7 here with the counter connected to the necessary logic gates with the A, B, and C connections used. And we have L3 and L4 at the bottom. So our current connection on the left shows A and B, but also not C. So the two conditions are A.B.C bar and B bar.C. So the A.B.C bar is already represented. We need to include some connections for B bar.C. So I've included here an AND gate, which will switch on if B is off and C is on. So connecting this in line with our first AND gate, remember that the code adds them together. So we can either have A and B but not C in one scenario, or C but not B in the other. So we need to use an OR gate here. And then this connects round to L3 and L4. And those are your correct connections. So your first mark will be for drawing the NOT gates in the correct position from B. Your second mark will be for drawing the AND gates in the correct position from C and not B. And by not B, I mean the signal from B after the NOT gate. And your third mark will be for the OR gate. So 3 marks there. Figure 8 shows the first stage filter circuit for a simple AM receiver. The circuit can be adjusted to resonate at 910 kHz so that it can receive a particular radio station. So we've got figure 8 there with the filter circuit. We've got 1.1 millihenries on the inductor and 1 picofarad to 120 picofarads on the variable capacitor. Calculate the value of the capacitance when the circuit resonates at a frequency of 910 kHz. So to answer this question, we need to write down the equation that links frequency with inductance and capacitance. I'll just add some labels there. So let's rearrange this equation to make C the subject because we're trying to calculate the capacitance. So we end up with C equals 1 over 4 pi squared F squared L. Now all we need to do is substitute in our values and make sure that you work in SI units without any prefixes. And that will give us a value of 2.78 times 10 to the minus 11 farads, which in picofarads is 27.8. So in terms of marks for this question, your first mark will be for the correct substitution of values into a correctly rearranged equation, and your second mark will be for getting the correct answer at the end. So 2 marks there. Draw on figure 9 an ideal response curve for the resonance circuit, labeling all relevant frequency values based upon a 10 kHz bandwidth. So we can see figure 9 there with relative voltage gain on the y-axis and frequency on the x-axis. Now the first thing to note here is that the peak of this curve is going to be at 910 kHz, which is the resonant frequency. As some extra reference points for this graph, we can say that because it's a relative voltage gain, the peak will be at 1. At a percentage gain of 71, or 0.71 on this axis, there will be a bandwidth of 10 kHz as stated in the question. So that will go from 905 kHz to 915 kHz. So from this, we can make a suitable curve. Now this is very difficult to draw by hand, but that's what the curve should look like. You can see that at 71%, there is a bandwidth of 10 kHz. So in terms of marks for this question, your first mark will be for getting the correct general shape of the curve and making the curve peak at 1.0. Your second mark will be for getting the correct bandwidth of 10 kHz at 0.71 gain. And your third mark will be for correctly getting the positions of those frequencies 905, 910, and 915, and showing to the examiner that you've identified them. So you'll notice I've just used dotted lines. So 3 marks there. The Q factor for the practical tuning circuit has a smaller value than the ideal one assumed in question 3.2. Discuss the changes the listener might notice when tuning to this station due to the practical Q factor being smaller. Now this is more of a factual question. There are a range of points that you can make, but you just need to select two. The two that I'm going to include here are a greater amount of noise, so that kind of static hissing sound that you get from a radio, there'll be more of that. That would be your first mark. And the second point could be that you get more crosstalk from neighbouring stations on that spectrum of frequencies. And that could be your second mark. I'll include some other examples of points below. You could talk about less selectivity, a lower amount of gain because there's loss of energy. And you could also say that there'll be a broader bandwidth. And each of those 3 points could also be worth a mark, but 2 marks maximum there. A photodiode forms part of a light meter used for checking light levels in an office. Figure 10 shows the circuit diagram for the light meter. So as you can see in figure 10, we've got that circuit diagram with our photodiode, not to be confused with an LED, which is a light emitting diode. Notice how the arrows are in opposite directions in each component. State the mode in which the photodiode is being used in figure 10. Now the answer to this is photoconductive, as opposed to photovoltaic. We can see it's photoconductive because there's an output between the photodiode and a separate resistor. If the photodiode was connected directly across an output, then it would be photovoltaic. So you'll get 1 mark for correctly stating that. In which mode is the operational amplifier being used in figure 10? Tick the correct box. Now the answer to this is that it's being used as a comparator, and the reason for this is that it's being used to compare 2 voltages with each other. So you'll get the mark for selecting the correct answer, but you don't need to write anything extra down. Figure 11 shows an extract from a datasheet of the characteristics for a photodiode under different light levels measured in lux. So you can see that graph shown in figure 11 with a range of different lux values and their associated lines. For a particular lighting condition, the current through the photodiode in figure 10 was 0.10 milliamps. Estimate, using the information in figure 11, the light level needed to cause this reverse current through the photodiode. Now, as we can see on this graph, if the reverse current is going to be 0.1 milliamps, then the most appropriate line is going to be the 1000 lux line. So really this question just requires you to read a value from a graph. So the light level here would be 1000 lux. And the only way to get that mark is to get the correct answer within a plus or minus 10% tolerance. Calculate the voltage at point X in the circuit shown in figure 10 for the light level in question 4.3. So let's go back to the diagram. So point X is here in the circuit, and the resistance we're interested in is 20 kilo ohms, and this will give us the potential at X. So we need to use the equation form of Ohm's law. So let's write that equation down first of all, with some labels. So all we need to do is multiply the current of 0.1 milliamps by the resistance of 20 kilo ohms, and that will give us 2 volts. So your only mark here will be for getting the correct answer. The 10 kilo ohm linear potential divider shown in figure 10 is set to give 1.75 volts at point Y. Assume that the operational amplifier has ideal characteristics. Deduce whether the output LED would be switched on or off when the current through the photodiode is 0.10 milliamps. So let's go back to the diagram. So it states in the question that at point Y, the voltage is 1.75 volts. That will then mean that the voltage at the negative terminal is larger than the voltage at the positive terminal, which means that the outputs will have a voltage of 0 volts. Now looking at either sides of the LED, we can see that we've got 5 volts on one side and 0 volts on the other. This potential difference is applied in the correct direction as well, so this LED will switch on. Let's write that in the answer space. So the first thing to say is that if the voltage on the negative terminal is larger than the voltage on the positive terminal, then the output voltage will be 0 volts. And that will be your first mark. Your second mark will not just be for stating that the LED is on, but explaining why, i.e. that there's a voltage drop across the LED. And that would be your second mark. So 2 marks there. Discuss how long wave, or LW, short wave, SW, and microwave links can be used to communicate beyond the visible horizon. For each link, you should give a typical carrier frequency that is used an explanation of how the signals travel from the transmitter to the receiver, and a typical use. You may use a diagram to help make clear aspects of your answer. Now, the best thing to do here is go through each type of communication and go through each of those 3 bullet points. We don't need to compare them to each other. So let's start with long wave. The frequency range is between 150 kHz and 300 kHz. Using the wave speed equation, we can calculate the wavelengths. And for a long wave, this range is between 2 kilometers and 1 kilometer. Now, for a long wavelength such as this, we can actually diffract the wave around the surface of the Earth. So we call it a ground wave. We should also state the typical use. One of those uses is national radio. So that would be sufficient information for long wave. We now need to repeat this format for shortwave and microwave. So shortwave has a frequency range of 3 MHz to 30 MHz and a wavelength range of 100 meters down to 10 meters. This wave reflects from the ionosphere, which is in the upper atmosphere, and is used in long-distance communications for ships and planes. Again, we've got the factual information there with the frequency range, a calculated wavelength range using the wave speed equation, a decent understanding of how the method of transmission works, and then an example of a use. So let's do this one more time for microwaves. Now for microwaves, we have a frequency range of 100 GHz to 2 GHz. I realise this time we're going from the upper limit to the lower limit, but that's fine, it's still a range. And then a wavelength range of 3 millimeters to 150 millimeters. Now this wave has to travel in straight lines, so all emitters and receivers must be within view of each other. So an example of this could be between satellites which are in orbit. Now an example of this could be in satellite television or a 3G phone network. So you'll see that for each of these 3 methods or types of wave, we have a frequency range, a wavelength range, a mechanism of transmission, and a use. Now if you've got that for each of those 3 types of wave, then you're likely to get 5 or 6 marks. If you've got this level of detail on 2 of those rather than 3, then you'll get 3 or 4 marks, and then it scales down from there. It's also worth noting that if you've got each of the 3 types of wave covered in very minimal detail, then you're only on track to get 1 or 2 marks. The mark scheme doesn't specifically outline a quality of written communication mark, but for 5 or 6 marks, it says that you need to use technical terms correctly. Remember that you can also draw a diagram for any of these 3 types of wave to illustrate your point. But this is a model 6-mark answer.